graduate research assistant at Kansas State University. Jose will be presenting on leveraging micro-ROS for enhanced communications in autonomous agricultural systems. He will discuss using micro-ROS with CAN FD for device communication and compare it with high-level CAN protocols like J1939 and CANOpen. As a proof of concept, he will showcase this approach in the sprayer subsystem of his autonomous agricultural robot. So please welcome Jose, and it's your turn.
Hello, everyone, and thank you, Lara, for inviting me to present. Can you hear me okay?
Yes, but I think no, the sound is not very good. Maybe the microphone...
I can talk louder. Do you hear better now?
Well, I think it's enough. Don't worry.
Okay. I'll make sure to speak very, very loudly. Thank you for the invitation. So let me share my screen so I can show my slides. So
No, not yet.
Not yet? Okay, let me try again. Now?
Now, yes.
Okay.
I think.
Can you see it full screen now?
Yes.
Okay.
Yes, now we can see the screen.
Okay, perfect. So my name is Jose Mateus Wrights. I am a master's student in electrical and computer engineering at Kansas State University. I will be graduating in 1 month. And I specialize in embedded systems and recently in computer vision, specifically for this project. I'm doing my project for Farms Lab, which is a precision agricultural lab in Kansas State University under Dr. AJ Sharda. So that's where I do my research in. So when I started working in that project, besides embedded system, I also work with computer vision, like optimizing models to deploy it in like an embedded Linux system, such as the Jetson. We use a NVIDIA Jetson Orin, and doing like a hardware accelerated image pipeline. So that was a big new to me, but I also was working in that since like a year ago. So I have experience in that and in the embedded systems, which is what I did mostly before that. So our project is under CANOpen autonomous pesticide spraying rover, right? And you can find a link to the project and to our site down below. So the purpose of this project is to apply pesticide only in infested areas to optimize the use of pesticides and also reduce the use of chemicals as less as possible. So we are working on a team of 3 people, and you can find those people as well in the link below, because I need to give credit to my team because I have someone working on the navigation system. I have someone else working with in the sprayer system, and I'm doing the embedded and the computer vision. So it's a very big project, and we are in process of patenting this because we would like to take it to the industry. So to begin, like how I came out with this using CAN as a transport layer for micro-ROS, let's start talking about why I needed micro-ROS in the first place, right? So we can see the bigger picture. So this robot is a prototype. You can see it's a rough prototype. So my NVIDIA Jetson, where I have ROS 2 running, is here in this box here. And the sprayer system is all the way here on the back, right? So we needed to integrate the sprayer system into our ROS system, right? But we have all of the solenoids to apply pesticide here. We have the pressure sensor here, the tank level sensor here. We have a liquid flow sensor here. So all of the sensors in the sprayer system is here, right? And I could integrate those sensors directly into the O-ring, into my Jetson O-ring if I really wanted to, right? But I wanted to distribute the system a little bit. Like I didn't want to bring, I don't know, a bunch of cables for each sensor up to that box. So I wanted to distribute my system a little bit. So I thought that we have different options. Like I could have put an embedded Linux computer here and just connect that to the Jetson and have ROS2 working with directly. But that would have been a little bit overkill for this type of situation, right? So we decided to just use a microcontroller, right? But then we needed to communicate that microcontroller with the Jetson, which there are different options. Like in that case, we needed to choose which communication protocol we will use in the physical layer, what we will use for serializing and deserializing the data. So those were questions that we had, and we ended up deciding to use CAN FD as our physical layer and leveraging micro-ROS for the higher level, right? Since we are already using ROS for our system, it makes sense to use micro-ROS, right? But let's talk about why we chose CAN. So I will briefly explain for the people that are not familiar. CAN is a communication protocol. It's called Control Area Network. So it's a twisted pair. Cables CAN high and CAN low, and they are terminated by a 120 ohm resistor on each side. So it's a daisy chain topology. So at the end of each side, you have a termination resistor. So CAN is the physical and the data link layer, and then in the higher levels, you have higher CAN level protocols such as CANOpen, J1939, and other ones that we will discuss a little bit of that later. But why CAN? So the reason why we chose CAN is one is the robustness, right? So it's a differential pair which provides very good robustness against like very electrical, noisy environments, harsh environments, plus all of the arbitration and error detection that the CAN has already in hardware. So to use CAN, you need your microcontroller or your microprocessor need to have a CAN controller, which a lot of microcontrollers and microprocessors these days already have a CAN controller built in inside the processor, right? And then you need a CAN transceiver. The CAN transceiver converts takes the CAN RX and TX signals and converts that to the differential pair. Is just a inverted differential pair is two inverted signals, and so we have different CAN specifications along the line and revisions. The most popular is CAN 2.0B, which supports up to 1 Mbps bit rate and 8 bytes maximum payload per frame. So you can have each CAN frame is the message you send has a ID. So you can CAN 2.0B added the possibility of extending the CAN ID because before it was only 11 bits. Now you have the classic like the 11 bits, but also you can have a 18-bit you can extend that up to 29 bits in total, because you have 18 bits to extend the CAN ID. And then we also have CAN FD, which means CAN flexible data rate. It now supports up to 8 Mbps bit rate, and you can send 64 bytes of payload versus 8 bytes, which is what the CAN 2.0B can do. This is very good for using as a transport protocol because you avoid a lot of overhead if you only send 8 bytes packages. But still, CAN 2.0B is I think is more popular these days still. But CAN FD is being adopted even more. The reason why 2.0B is more popular still is because high-level protocols like CANOpen and J1939 are still using that. Now they are coming with new versions that can use CAN FD as well. Then we will talk about the high-level protocols. So we have J1939. This is a set of standards of how ECUs, these are electronic control units that you have distributed around a system. It can be a tractor, a heavy-duty system, car. So it's a set of standards of how this ECU communicates, but specifically for heavy-duty vehicles. So it provides a common language that manufacturers can use because it's defined instead of having to deal with different proprietary OEM specific protocols. And I won't go too much in detail about J1939 and CANOpen. I'll just give a brief overview, but I invite you to look more about it because it's very complex. Like it's a whole different beast. They're very complex systems, very powerful system. They have a lot of tools, but this is mostly used for heavy-duty vehicles. So if your application is not related to that, then it might not be the best option for you to use. It might not fit very well. Then we have CANOpen. CANOpen has more, it's more general than J1939, and it defines also how different nodes in a CANOpen, because in CANOpen you have different nodes, how the nodes communicate and how the data is defined. And also the good thing about CANOpen is that there are some profiles. For example, CIA. So CIA is the organization that manages CANOpen, just like SAE is the organization that manages J1939. So CIA means CAN in automatization. So, for example, the 401, I think it was a 401 profile, is for motor controllers. It defines how motor controllers work, the messages they send, the services they have. So that's also like a standard. So you can use different motor controllers from different vendors or several motors, and if they are CIA 401 compliant, the interface will be the same. But you can also define your own way of your own dictionaries to communicate with the nodes. But then we ended up deciding to use CAN FD as a transport layer, right? Because these two are the high level. CAN FD is the physical layer. These two are higher level protocols on top of CAN, right? But they use CAN 2.0B. Now they are releasing versions with CAN FD. So why we decided to instead just use CAN FD as a transport layer and have microROS to leverage all of the the communication, the high level part, the serialization, deserialization, everything. So one is we wanted to use CAN FD as our physical layer because of the reason I specified before, because of the robustness. Also, I can add more devices into the bus later down. If I use serial, I will need to, if this, like I cannot use just TTL signals in a very long cable, I will need to use RS-232. But then for every micro-ROS client I want to add, I need to add another serial connection. Ethernet is also an option with UDP packages, but it makes the hardware a little bit more complex. So in CAN, I can drop the devices in the bus, right? So that's the reason why for upgradability, flexibility. And also the micro-ROS agent already supports CAN FD as a transport layer. So in my application, I wrote my micro-ROS system with Zephyr RTOS, because that's what I like to use for embedded systems, for RTOS. So what I did is just I wrote the CAN FD transport for micro-ROS, because right now the micro-ROS Zephyr module doesn't have that. I want to push that to the micro-ROS Zephyr module repo, but since micro-ROS only officially supports Zephyr 3.1 and I'm using Zephyr 3.5, the CAN API is different, so I need to make it backwards compatible with Zephyr 3.1 before I can push that. But if someone is interested in my in my GitHub, I have a fork of micro-ROS Zephyr module, and I will push the CAN FD transport when we finish this meeting, and then I will byport it to 3.1 and try to get that merged into the upstream micro-ROS Zephyr module. So what are the pros of doing this, right? This is my system right now. I have my Jetson with a CAN transceiver. It actually has a CAN transceiver as well in the PCB. And then connect to STM32. The STM32 has a current and voltage sensor in the power bus for the sprayer. It has external ADC connected to a pressure sensor. It has a flow meter. It has an ultrasonic sensor, which is what we are using for the liquid level. And then we have another CAN bus connected to an ECU for that, an ECU that controls solenoids, so we can spray. This might later be integrated directly into this system. So we have another CAN bus to communicate with the ECU with the CAN 2.0B. The ECU then connects to another module called the driver, which drives the solenoids. So the pros of this is that you have access to all of the ROS2 tools once that you have micro-ROS running. You don't have to worry about how to serialize, how to decode messages, because even in J1939, you need to decode the messages, right? But you don't need to do anything like that. It's pretty much plug and play once that you have your micro-ROS working. You just go and your ROS2 system and you run the agent and it will show up. So that's adds so much flexibility. It's so much seamless. It's pretty much is the benefit of having DDS in your system. It's just how well integrated and how easy it makes it, how clean it is. So that way you don't have to spend time, dealing with the communication part and just focus on your application. Then what are the cons? The the cons are right now that, as far as I know, if you have multiple devices, multiple micro-ROS clients, if they want to talk to each other, they still need to go to the agent first, and the agent forwards that message to another client. So clients cannot talk directly. As far as I remember, might be different now. So in J1939 and CANOpen, different nodes can talk directly to each other. But you have also different type of networks that you can choose in J1939 and CANOpen. So, and also you need a micro-ROS agent. You cannot just run a microcontroller. You need to have an agent somewhere. So that the content also like is not like J1939 CANOpen has years of trial and certifications and all those stuff. So to use kind of like to get to that part using micro-ROS, there has to be a lot of certifications, a lot of feasibility tests, know how deterministic are the messages, depending on the application, right? In our case, since we are spraying, nothing happens if a message is a little bit delayed, but if we are talking about controlling a motor or a vehicle, then things are different. So this is a screenshot of when we were testing our system. So this is sprayer pressure and sprayer tank level are coming from here from the micro-ROS system. So then we easily with micro-ROS we can synchronize time between the agent and the client. We can then timestamp the ROS messages, and it's so seamless. And another problem is that you have to be mindful of how the data you send. While using micro-ROS, it's easy to just forget that you are in maybe an embedded system and try to send just ROS2 messages. So such as like sensor message, like the standard sensor messages and such. Sometimes those messages are too big. Like the IMU message is very big. It has a covariance matrix, two covariance matrix of size 9 of float 64. So that's a lot of data. So sometimes you might need to create your own custom message, and in your ROS side has another node that converts that back into a standard ROS2 sensor message or whatever type of message you're using. If the messages you are trying to send are too big, so maybe you might need to breed some of those stuff. And in like J1939, a lot of the messages are, for example, for example, the vehicle speed is a byte, which you later, when you decode the message, you scale by a factor, and then you have the value in the appropriate unit. But in ROS messages, we use a lot of floating point and stuff like that, so we have to be mindful of that. So why do we need this, right? So the purpose of the project is, see, these bugs here are aphids. So we are trying to identify the aphids on the plant, right? And then spray where the aphids were detected. So right now we are using just a 2D camera, and I'm doing some image geometry to estimate what's the position of the aphid in 3D coordinates with respect to the world. And it's accurate enough for us to spray in the infested area. So that's our robot, that's our camera. These red dots here are the aphids in 3D coordinates, and this is the detection image. So I also wanted to talk about something interesting is the CAN ISO TP. So it's an international standard for transfer of data packages via CAN. So TP is transport. But it allows you to send bigger package size through the CAN bus. So it says like up to 4 gigabytes per message. But it actually is using CAN 2.0B or CAN FD on the back. And it's just dividing a large data into different CAN frames and then combining that together. It's doing something similar to what the CAN to what the micro-ROS client and agent are doing. So sometimes you will send in micro-ROS, well, we use CAN FD which has a payload of 64 bytes. A lot of the times we send messages that are bigger than that. So, the micro-ROS is micro ArcCSD, DDS is, dividing and packaging all of those data and then combining that on the other end. So this is doing something similar. But something interesting is that there is a package called ISO-TP tunnel, or ISO-TP tunnel, which is including the CAN utils package in Linux, which allows you to create a UDP or TCP, a UDP and TCP tunnel between two computers running Linux, right? So I watched a video of someone like routing internet traffic from one computer to the other through the CAN bus. And I was inspired to do this, but see if we can use ROS2 between two different Linux computers with ROS2 running fast DDS. So I tried that last night. So I have my desktop computer with a CAN probe connected to a Raspberry Pi. I cannot grab it. Which also has a CAN controller and CAN transceiver. So my computer to a Raspberry Pi through CAN. And I run this CAN ISO-TP tunnel, which created a virtual network interface. And I tried to see if ROS2 will work between, and I disable Wi-Fi in my desktop computer. So see here, I'm pinging the Pi through the CAN Ethernet interface. The CAN network interface. So see, this is the interface called C tunnel 0. So now I will SSH to my Pi from my computer through that CAN network interface, and it works. So this terminal now is my Raspberry Pi. This is my desktop computer. And here I will launch a node, an IMU node. And let's see. So here I'm showing that Wi-Fi is disabled, network is disabled, like Ethernet is disabled. Only the CAN network interface is working. So here I will launch a node and SSHing into my Raspberry Pi through the CAN Ethernet. So here I launch an IMU node in my Raspberry Pi. And here we'll do a CAN dump just to see all of the CAN messages in that CAN interface. Now the IMU data show up in my ROS running here in my desktop. It's being polished by my Raspberry Pi. Now it takes a lot to subscribe or to do topic herd. Let's see, I can get the data. So this is very interesting. in case that you want to have different Linux computers running ROS and you want to have them connected through CAN, because like I said, the hardware to run CAN is much simpler and cheaper than Ethernet. The Ethernet, you need either multiple network interfaces or you need a switch, and this is just a transceiver and you basically change all of the devices. Of course, this ISO-TP tone package, even in the GitHub from the author says that it's a proof of concept, so it should not be used in production, but it's just this is just a proof of concept and open up the conversation to pay more, to develop more uses of micro-ROS or ROS2 as well with CAN FD as a transport layer, like having the DDS and ROS2 support CAN natively, and do more tests in CAN using micro-ROS with CAN FD, because there are a lot of tests that I would like to do, but I didn't have the time because of all of the projects, all of the work I have to do in this project, because this is just one, the micro-ROS is just one part, like the computer vision takes a lot of my time as well. So something I wanted to try and didn't try is having multiple micro-ROS clients on the same CAN network and see how the agent works in that case. So, because the beauty of CAN is also having multiple devices in one network to simplify wiring. So see, this IMU was polishing at around 104 hertz. Here I can only get like 13 hertz, and this is, well, I got up to 17 later, but that's and I was running the CAN at, I don't remember if 1 Mbps or 500 kilobit per second. But I also there are some parameters that I need, like you can set in the ISO-TP tone that I didn't really play with. So maybe we can get faster speed, but it's just interesting that you can, SCP files, SSH, use fast DDS through a CAN network interface with this ISO-TP tone package. So here is a demo of my, to finalize, this is a demo of my system. You might not see the display running, but this is a test we are going to validate the system. So we can successfully, we have a service in micro-ROS to trigger the solenoids. I can do a quick demo to finalize. So, can do a quick demo to finalize, but so the micro-ROS is my micro-ROS system is in my robot, which I don't have with me right here, but I can do so. In that we have all the sensors and the services to trigger the solenoids. So here what I can do is I have my development board, STM32, and I have a CAN probe connected to my computer. So we can just launch micro-ROS through this. This STM32 is connected through CAN. It's blurring the cable. So here, this is the twisted pair cable used for CAN. It has an impedance of 120 ohms. Then you terminate each side with 120 ohm resistors. If you can see it, it's connected to my CAN probe to my computer. So here, let me pull up the serial terminal so you can read the messages from my microcontroller. So now I launch a micro-ROS agent with the CAN in the CAN interface. So then I will reset my microcontroller, and now this is working. So I'm just printing this when there is a callback for pressure data already. Also, something I like that I have in my micro-ROS system is the possibility to ping the agent when you want to start a micro-ROS. That way, if the agent is not ready, I can ping and just wait until the agent shows up. So I have that here. We just didn't see it. Okay, so and then this is my computer running ROS2. I'm going to do ROS2 list. We have the sprayer node and then ROS2 topic list. So we have sprayer pressure. So like I said, in my robot, I have all of the sensors. In this one, I only load up the pressure sensor, which I don't really have a pressure sensor in here. It will just publish the data from the ADC, but I don't even have a sensor connected to the ADC, so it will just print garbage. But we can just see those two topic echo. So here it's printing just the value from the ADC, which doesn't have anything connected right now. But cool things like I have the timestamp, which is synchronized with the host. So that's when we record ROS bags and we want to debug, this is very helpful. So this is a ROS2 sensor messages, fluid pressure message type. And let's do see what's the frequency. So it's 775 hertz. In my robot, I would just run it at 100 hertz. This is just for demonstration purposes. So that's it. Like I said, there's a lot of work still to do to have micro-ROS working with CAN FD is reliable, but I mean to polish it, to use it in larger ag systems. But it's definitely possible, and I just wanted to open the conversation to consider that. And we need industry to be interested in that, so a lot of development effort can be put that and can be validated, as well as using something like the ISOTP tone that I just showed before to have ROS2 with just VDS working through CAN. I think that's fascinating, and it opens so much possibilities for large agricultural systems. So that's what I wanted to present, and I really appreciate your time and that you joined.
I'm in mute. Okay, thank you very much, Mateus. Does anyone have a question for him?
Can I go ahead, please?
Yeah, go ahead.
Okay, thanks, thanks, Matthias, for the nice presentation. I can assume that this was a lot of work and a lot of pulling out your hair, especially with all these automotive protocols and ROS. And I had a question regarding, I think I had a few questions. Maybe I'm not even asking the right thing, but I'll just try. So forgive my amateurness if there's any. I wanted to ask if so the bridge that is between the micro-ROS agent and the micro-ROS client, which is between the Jetson AGX and the STM32. Have you ever run any stress tests or any bandwidth benchmarks between the two as to how much information can be exchanged. Maybe just in case, let's say, if you had a LiDAR or something attached to your STM32 and you really care about bandwidth, like would you have any number on that?
Not quantitative. Like I did run stress tests, but not in like a very technical quantitative way. It's just because of like the amount of work we are doing. Like we are moving fast in this prototype. That's a great question. That's a great question. Something I wanted to do is have a time of flight sensor, for example, to start with, so you can distribute those around the robot. I was thinking to make a PCB of one with to put a like, very small microcontroller and a CAN interface, so we can put it in GitHub so people can get it fabricated. But no, I did not like what I did is I run all of my sensors, like the tank level, the pressure sensor, the what else did I? Yeah, it was that for now, and well, I also have the service to set the solenoids, to trigger the solenoids. So all of my sensors were working on the appropriate rate, and I didn't like did any smaller, I don't know, compact version of my messages. I use like the standard ROS messages with like frame ID as a string and everything, and so I was able to get like 100 hertz in both of them. I run something I did is I run the just int int32 with CAN FD as fast as possible, and I will get 1000 hertz. But then when I compare that using serial and USB, I will get like half of that. So I get better speed with CAN FD. But that can also be the driver in Zephyr of how serial and USB is being managed. But that's a great question. Like I think we should do. That's what I was talking about. Like in the presentation, do more extensive tests of bandwidth and so forth. If you will have a lot of devices in your CAN network.
Sure. Wow, thanks, Matthias. Can I ask you one more? Would there be time for that?
Sure.
Okay. One more question was that have you been tweaking the QoS while doing any of these transport protocol tweaks? Like, does ROS does the DOS work out of the box with the default quality of service, or do you think that changing the default is crucial in using the CAN as a bridge?
For micro-ROS, I didn't really test the DDS. Well, what I did is in the micro-ROS itself, sometimes some of my messages I changed the quality of service from reliable to best effort. To be honest, in CAN, I didn't need to do that. Even with reliable, I won't lose packets. I will have a full frequency. When using UART or USB, then I needed to specifically use best effort. Otherwise, you want. But I think that's more to do with the Zephyr drivers.
Okay. That answers my question. Yeah, that's perfect. Thanks for your presentation.
So I have a question here in the chat from Adrian Fernando Chavarro, asking if the CAN use if I have noticed any influence of environment in the protocol performance. Yes, a little bit. Is that like depending on how long the cable is, you have to be more careful. You have to be with your impedance, like to make sure that you are terminating the correctly. That you don't have when you will break your your daisy chains to connect to different devices. This stop should not be too long. Like we have calculations, but if I'm running at higher speeds and it's not the impedance is not terminated correctly, or you have long stops, or you are not even using. Sometimes if you are running a low bit rates and your devices are too close, you can use a normal cable, not a 120 ohm differential pair. Not recommendable, but for testing here in your desk, you can do that. But I noticed like sometimes it will, if I did like very sketchy setup with no terminating correctly, it will drop packets for sure. Yep.
Anyone else? Okay.
Feel free to reach out by email or LinkedIn if you have more questions as well. I will be presenting I forgot about this. I will be presenting two publications at two research in the International Conference of Precision Agriculture, it's called ICPA. And this year will be hosted here in my university. So if everyone is interested in coming, please message me, and I'd love to meet you.
Okay. Thank you very much.
Thank you.
Wish you the best. So thanks a lot, Mateus, for your presentation. Very interesting. And well, if someone else wants to present here on another session of the working group, please email me. So that's everything. Thanks a lot, and see you next month. Bye.
Bye-bye.
A lot of very quick question. Is the recorded presentation, will you be sharing with people or not?
Can you repeat, please?
Will you be sharing the recorded?
Yes.
Okay.
Yes. I don't know if this week, but next week for sure. I will. Yes, we will share on our LinkedIn and also in ROS Discourse.
Okay. Awesome.